In this video, we're going to learn about related rates problems. So first, what are related rates and related rates problems? These are where we want to somehow relate the rate of multiple varying values. And if this doesn't make any sense, I'll wait till the examples. I have 4 of them. You can skip to them down below if you'd like. But before I go into those, let me give you the general plan, the steps we're going to do. So the first thing I always do is write an equation that relates all varying values, or all pertinent values, all important values. Second thing, take the derivative, usually with respect to time t, to relate the rates. A note for this, so before we can only substitute constants. I'll explain that more fully when we get to an example, but once I write this equation, I can put in the constant values, then take the derivative. After I take the derivative, then I can substitute all values and solve the problem. So let's see a couple examples. They'll go sort of from easy to difficult. First example, you're filling a giant spherical water balloon at a rate of 100 cubic inches per minute. When the radius of the balloon is 20 inches, how quickly is the radius of the balloon increasing? So, first thing, write the equation. V equals 4/3 pi r cubed. The volume is increasing, so I can't put a value in for the volume. The radius is also increasing, so I can't put a value in for the radius. Pi and 4/3 are constants, so I'm not going to mess with those. And so from here, I take the derivative of everything with respect to t. So the derivative of v with respect to t is just dv dt. The derivative of 4/3 pi r cubed, well, I bring the 3 out and multiply it. 3 times 4/3 is 4. I'm left with pi r squared. And since I'm taking the derivative of this r with respect to t, I need to use chain rule, and I still have a dr dt. At this point, I can plug everything in. So I'm filling the balloon at a rate of 100 cubic inches per minute. So it's increasing at that rate. That is dv dt. I have 4 pi. The radius is 20, so I can put that in. And I want to find how quickly the radius is increasing. That's dr dt, so I'm going to solve for dr dt. 20 squared is 400, times 4 is 1,600, so I have 100 equals 1,600 pi dr dt. I'll divide both sides by 1,600 pi. Those cancel. The 100 divided by 1,600 gives me 1/16 pi. And that's going to be the rate of change of the radius with respect to time. And I guess I could say the radius is increasing at a rate of 1 over 16 pi. Units on that are going to be inches per minute. Before I go on to the second example, a quick explanation as to why I can't put in V or R here. So if I put in the value for R here, put 20 in here, I'd have V equals 4/3 pi times 20 cubed. And this is going to be a constant. Since it's constant, when I take its derivative, it will equal 0. But we can see that I actually have something varying here. The volume isn't changing at a rate of 0. It has to be increasing. So that's the idea. I can't actually put in any of the values that happen to be changing over the course of time. Radius and volume are both increasing, so I have to take the derivative before I can put anything in. Example 2. Two cars are on perpendicular roads. Car A is 25 meters north of the intersection, traveling north at 10 meters per second. Car B is 60 miles west of the intersection, traveling 5 meters per second east. How quickly are the cars moving toward or away from each other? So first, I'll draw the roads. So we have two perpendicular roads. I have my two cars. So car A is 25 meters north. So that's an A. 25 meters. And it is traveling north at 10 meters per second. So I'll put a little vector. 10 meters per second. Car B is 60 meters west of the intersection. So there's B. There's a 60 meters. And it is traveling 5 meters per second east. And so, how are we going to figure out if they're moving toward or away from each other? Well, this can be modeled by a right triangle. So, there's the 60 meters. Here's the 25 meters. And I want to know if the cars are getting closer or farther. That is this hypotenuse. And so I'll start by writing an equation that relates these. So we'll have a squared plus b squared equals c squared. A is changing because the 25 is getting larger, so I can't put in 25 yet. B is changing because the 60 is getting smaller over time, so I can't put in 60 yet. C will probably be changing itself because both A and B are moving. It might not be changing, but in this case it is. So I can't plug in anything, so I'll take the derivative with respect to t. And that will give me 2a dA dt plus 2b dB dt equals 2c dC dt. To simplify the computations a little bit, I can divide everything through by 2 and get a dA dt plus b dB dt is equal to c dC dt. And now let's start looking at this. So I want to find dC dt. I want to find how quickly this is changing. I know that A is currently 25. I know that dA dt is positive 10, so let me put that in. So A is 25 meters. And dA dt, since A is getting larger, I'm moving away from the intersection. This will be a positive 10. I know that B is currently 60 meters. And I know that dB dt is actually a negative 5 because B is getting smaller over time. B is moving toward the intersection. Unfortunately, I need to know C, so I only have one variable, this dC dt, left over. But that's not too difficult. I can just do Pythagorean theorem and just consider, okay, 25 squared plus 60 squared equals c squared. Either I notice that this is a 5, 12, 13, so this will be 65 meters. Or I can go through and do this. 25 times 25 is 625. 60 times 60 is 3,600. 625 plus 3,600 is 4,225. And the square root of this will be 65. It better be 65. Let's just check to make sure I'm not crazy. Square root of 4,225. Good. All right. So I can put that in here. 65 dc dt. And now I just do the computation. So 25 times 100 is 250. 60 times negative 5 is negative 300. 250 minus 300 is negative 50. And when I divide by 65, so dc dt will equal negative 50 over 65, or dividing the numerator and the denominator by 5 gives me negative 10 over 13. So wrapping this all up, sort of writing out the answer, I can say the cars are moving toward each other. They're getting closer. The reason for that is the rate of change is negative, so the distance is getting smaller. So they're moving toward each other at a rate of 10 over 13 meters per second. So a very slow rate, but they are moving toward each other. 2 examples down, 2 examples to go. You're standing 1,000 meters away from the launch pad of a rocket. The rocket is traveling vertically. What is the angle? When the angle of elevation from you to the rocket is 0.4, no units here means we're dealing with radians, you notice that it is increasing by 0.025 radians per second. How fast is the rocket climbing? So in this, let's make a green rocket. So we have this rocket. Look at this lovely rocket. Let's give it some fire. All right. And we have you. Let's make you blue. And in here, we have another right triangle. We know that this distance is 1,000 meters. We have this angle here, and I want to figure out how the height has changed, so I'll put a little h here. And so what this means is the equation that relates all of the pertinent variables is tangent of theta is equal to h over the adjacent, the height over the adjacent. But in here, you're not moving. This 1,000 meters is not changing. It's a constant. So I can actually save myself a lot of trouble and quotient rule by realizing that this will just be h over 1,000. And now I can take the derivative. So the derivative of tangent is secant squared. I need to include a d theta dt because I'm taking the derivative of everything with respect to t. This is h divided by a constant, so the derivative of this is going to be 1 over 1,000 dh dt. And now I can just go through this work. So the current angle of elevation is 0.4, so I'll do secant squared 0.4. The rate of change of the angle of elevation, it's increasing by 0.025 radians per second. So I'm going to multiply this by 0.025 radians per second, and that will equal this divided by 1,000. So dh dt, I want to find how quickly it's going up. That is dh dt. So let me go through and evaluate this. I'll go to a calculator. In order to do secant squared, first I will do, let me make sure I'm in radians, so I am in radians. I'll first do the cosine of 0.4. I'll do 1 divided by that value, and I will square that. I'm going to multiply that by 0.025. I didn't do that properly. Let me try that again. So 1 over cosine of 0.4 squared times 0.025. And then I had to multiply both sides by 1,000, so I'll do that. So times 1,000. So that'll give me dHdt is approximately 29.469, or written in clear English, I can say the rocket is climbing at 29.469 meters per second. Alright, last example, and this is a fun one. Kind of ridiculous one, but fun one. You're given a point-down conical tank that is partially filled with hot fudge. Let me draw that. So we got this point down. Ooh, that's not going to be, it's going to be more like this. I know, big difference, right? Alright, it's partially filled with hot fudge. Let's see. It's not a great hot fudge color, but it's going to have to do. Alright, the radius of the tank is 15. So from here to here is 15 meters. The height of the tank is 10 meters. So from here to here is 10 meters. If the fudge is being ejected out of the bottom of the tank at 2 cubic meters per second, that's a ton of hot chocolate. I don't know if it's a literal ton, but it's actually not going to be that far off. It's going to be probably hundreds of pounds of hot chocolate every second. How quickly is the depth of the hot fudge in the tank decreasing when it is 6 meters deep? So in here, I guess it's worth noting that it's currently 6 meters deep. So let's do the work. I'm dealing with the volume of a cone because the hot fudge in this sort of tip of the cone will take on a cone shape itself. So V equals 1/3 pi r squared h. But notice, I'm never talking about the radius of the hot fudge, which is going to be less than 15. It's inside this tank. I'm always talking about the depth of the hot fudge. That's h. So the first thing I'm going to do is try to figure out how to deal with h in terms of r. So here's the r, here's the h. And I know that I have similar right triangles, so the radius of the tank, 15, divided by the height of the tank, 10, is going to equal the radius of the hot fudge divided by the height of the hot fudge. I want to get this all in terms of h, so I will solve this for r, because I want to know about the depth of the hot fudge. So 15 over 10 reduces to 3 over 2. I'm going to multiply both sides by h. And so what I can do with this is now rewrite this in terms of h only. So V will equal 1/3 pi times 3h over 2 squared times h. And I can do some work here. So 3h squared is 9h squared. 2 squared is 4, times 3 is 12, so I have 9h squared over 12. I still have this pi and this other h. 9 over 12 reduces to 3 over 4. H squared times h is h cubed, so I have 3h cubed pi over 4. And that's going to be my volume equation. Now I can do the work. So I can now take the derivative, dv dt, and the only varying part here is h cubed, so I take the 3 out, change the 3 to a 2, so I will have 9 h squared pi over 4. I need to include a dh dt because I'm taking the derivative with respect to t. And I can plug in everything now. So the change in the volume with respect to t, well, hot fudge is being ejected out of the bottom of this. So that means that this rate of change will be negative. So I have negative 2 equals 9. The current depth of the tank is 6. So I have 6 squared pi over 4 dh dt, because I want to find the rate of change of the depth. In here, 6 squared is 36 times 9. Let me be lazy but not mess this up, so 36 times 9. And I know that it will divide by 4. I could have done 36 over 4 and get, ooh, that'd be better than 9. 9 times 9 is 81. I guess I'm an idiot, but we'll do this anyway. Hey, look, 81, big surprise. All right, so negative 2 equals 81 pi dh dt. And just divide both sides by 81 pi, and so I get dh dt is equal to negative 2 over 81 pi. And so what this means is the depth of the hot fudge, so much hot fudge, is decreasing at a rate of 2 over 81 pi, and this is going to be in meters per second. I hope these helped out. Feel free to comment below if you do have any questions.